Hi guys, welcome to the second lecture in this summer course. So previously we have looked at what a differential equation is, and we also discussed what it means for the differential equation to have a solution and what a solution should look like. What we're going to do today is to begin to actually find solutions. Okay, so we're going to look at two techniques for finding solutions. We are only going to be focused for now on first order differential equations. But then some of the techniques that we're going to learn today can also be applied to second order differential equations, and I'll make that clear when we get there. But the most important thing that I would like to get across today is to show you a very basic analytical technique that you can use to solve a special class of differential equations, and then also a graphical technique that can be used for first order differential equations. Okay, so this graphical technique cannot be used for, say, a second order differential equation in the way that I would introduce it. All right. So these two techniques, with these two techniques, that you should be able to say something smart or intelligent about the solutions to first order differential equations. And then the final thing that I'm going to try to get across to you is a criteria that guarantees the existence and uniqueness of particular solutions to initial value problems. Okay, and so we're going to look at a theorem that tells us when we can expect an initial value problem to have a particular solution. And we're going to look at cases where, that theorem is not satisfied, and what we can expect out of those cases. Now, the idea of having, a unique solution to an initial value problem is very important for making predictions, right? So if you imagine that you have multiple, particular solutions to one initial value problem, then there are multiple paths that, the dynamics of a process can take. And so which path do you use to make predictions, right? So for predictive analysis, it's important that we have, one well-defined path, which will be our solution to the differential equation. And it's important that before we go ahead to do any calculations, that we can have a sense of whether, a particular formulation of the differential equation will have a unique solution or not. So this is a very important idea that I'll introduce. We'll go through some examples, and then that should be it for this lecture. Okay. All right. So let's begin with the analytical method for solving first order differential equations, and then we'll see how that can extend to second order equations. All right. Now we're going to consider first order differential equations in normal form. Okay, this is always going to be our starting point for at least these first 2 weeks. All right. So we know that if I put a first order differential equation with unknown function y of x in standard form or in normal form, right, then I can write this as dy dx is some function f of x and y. Okay, so hopefully you remember this idea, right? Now, in the event that my right-hand side function f is only a function of x, right? So if we assume that, if we assume that f of xy is just some function of x, then what we have for our first order differential equation is really dy dx is g of x. Okay, and so what are we saying here? We are saying that the derivative of some function is g of x, right? And if we know the derivative of a function and we want to find that function, then we can use just standard techniques in Calc 1, first semester calculus, to find an antiderivative, right? So in other words, I can define my solution to be the antiderivative of g of x dx. And this will be the general solution to our differential equation. Okay. Now notice that this can only apply when my f of xy is simply a function of x. which means that it only depends on the independent variable, and it does not depend on the solution that we do not know. Otherwise, it's going to be very difficult to carry out this integration process, right? So if you have such a situation, then you can go ahead and just directly integrate, and that should give you your solution to the differential equation. Okay. All right. So this process is called direct integration. Okay. So let's take an example here. Solve the initial value problem given below. All right. So notice that my f of xy is simply a function of the independent variable x, right? And this means that I can write my solution as the antiderivative of 2x plus 3 dx, okay, which we know to be 2x squared over 2 plus 3x plus some unknown constant c, right? And so my solution to the differential equation is going to be x squared plus 3x plus c. And this is our general solution. Okay, now notice here that we have a one parameter family of solutions, so that by specifying different values of c, we can generate the general solution. All right. Okay, so now if we want a particular solution, we're going to apply this initial condition and say that we would like y when x is 1 to be 2, which means that 1 squared plus 3 times 1 plus c should be 2, right? And so that implies that c is 2 minus, so that is 4, right? So that is minus 2, right? And so my particular solution is now x squared plus 3x minus 2. And this should satisfy both the differential equation and the initial condition. And that's all there is to direct integration. Okay. Most important thing is you can only do this if your f of xy is only a function of x in normal form. Now, it's important that you put your differential equation in normal form before you attempt to solve by direct integration, so that you can correctly pick out this, g of x and know exactly what it is. Okay. All right. So we're going to go through a few more examples. We're going to look at how this technique can be applied to solve second-order differential equations, which have the exact same form, where the right-hand side is simply a function of x. And then we'll look at how this applies to problems in motion, right? And how we can use this technique to solve problems in motion. Okay. All right. Okay, so let's take an example that will allow us to extend this method to solve second-order differential equations. Find the position function x of t of a moving particle with acceleration given, by this linear function here. We assume that we know the initial position of the particle, and we also know the initial velocity. Okay, so our goal is to find x of t, which is a position function, right? So the question is, well, where is the differential equation? Because right now we don't see any derivatives flying around. Okay. Now the thing to keep in mind is that acceleration can be expressed in terms of position by taking the second derivative of position, right? And so saying that my acceleration is 2t plus 1 is really saying that the second derivative of the position function is 2t plus 1. Okay, and so this gives us our differential equation. All right. Now notice that this differential equation it's in normal form because we have solved for the highest derivative term, and the rest of the equation is only in terms of the independent variable t. Okay, and so this allows us to perform direct integration. Right. Now we have some more information here. We are also told that the initial position is 4. So this means that x when time is 0 is 4. And then we are told that the initial velocity is -7. Now velocity is the first derivative of position. So this means that x prime at 0 is -7. All right. And our goal is to find x of t. Okay. Now the idea here is very straightforward, and you've done something like this in calculus. Hopefully you remember that. If I have the second derivative of a function, right, and I want to find the function, right, I can first apply direct integration, or I can just apply the antiderivative to move from the second derivative to the first derivative. Right. So I can calculate the x dt by taking the antiderivative of the second derivative, and then I can move from the first derivative to the function by applying another antiderivative. So you do 2 sets of antiderivatives, and then you can move from the second derivative to the first derivative. All right. So this is exactly what we do in this case. All right. So we'll first find the first derivative by calculating the antiderivative of the second. So this is the integral d squared x dt squared dt, right? And this is going to be the antiderivative of 2t plus 1 dt, right? Which gives us t squared plus t plus some constant c. So this is x prime of t, or dx dt. Okay. And then once we have dx dt, we can apply another integration process to get the position function x of t. So this is the integral dx dt, which is the integral of t squared plus t plus c dt. And this gives us t cubed over 3 plus t squared over 2 plus ct plus d. Okay. So my x of t is now t cubed over 3 plus t squared on 2 plus ct plus d. And this is the solution, at least the general solution, of our differential equation here. Okay. Now, a couple of things to take notice of here. Notice that in that general solution, we have 2 unknown constants. So we have c that has to be determined, and then we have a d that has to be determined. Okay, and so this general solution is no longer a 1-parameter family of solutions. This is now a 2-parameter family of solutions. Okay, and that is happening because we have a second-order differential equation. Okay, so remember that first-order differential equations gave us a 1-parameter family of solutions as a general solution, while second-order differential equations give you a 2-parameter family, and you can go on and on and on. Nth-order equations will give you an n-parameter family of solutions. Okay, so this is the reason why we have 2 initial conditions here, because we have 2 unknown constants that we have to find. Okay, so we're going to apply these conditions in succession, and then find out a particular solution for this initial value problem here. So first, I'm going to apply the fact that x when time is 0 is 4. So this gives me 0 plus 0 plus 0 plus d. This is supposed to be 4. So that implies that my d is 4. Right? And so now my x of t is t cubed over 3 plus t squared over 2 plus ct plus 4. Okay, now that leaves us with 1 constant to determine, which is c, and we're going to apply the condition in terms of the velocity to that. All right. Now x prime of t, we already have x prime of t right here. And so we're going to use that to find c. So we'll say that, oh, x prime of 0 is supposed to be minus 7. And so using the equation for the first derivative, we know that this is 0 plus 0 plus c. This is supposed to be minus 7, which implies that my c is minus 7. Right? And so my particular solution is now t cubed on 3 plus t squared on 2 minus 7t plus 4. And we have found our particular solution. Okay. Right. So, and we can do this for a third order differential equation that has the exact same form. Okay. Where, once you put it in normal form, the other side of the equation is just a function of the independent variable. We can use successive applications of the integration process to find the unknown function, and then go ahead and apply whatever initial conditions we have to calculate the particular solution. Okay. So how many initial conditions do you think we will need if we had a third order differential equation? All right. Yes, 3. Right? Because we expect that a third order differential equation will give us a 3-parameter family of solutions. And so we'll need 3 initial conditions to find a particular solution. Okay. All right, good. Okay. So now that we kind of have an idea of how to formulate a differential equation in a motion situation where we know the acceleration and we want to find the position. Now let's go to kind of something that is a bit more real in terms of the application problem, something that we can hopefully visualize, and then we can kind of break down into a differential equation and then solve using direct integration. So this is our third example here. This is also an application to motion. A ball is thrown straight downward from the top of a tall building. All right, so let's make a little illustration here. This is my building, and I throw a ball down. So this ball is going to fall. Okay. The initial speed of the ball is 10 meters per second. Right, so this ball begins to fall at 10 meters per second. It strikes the ground with a speed of 60 meters per second. Okay, so once it gets here, it is moving at 60 meters per second. Now the question is, how tall is this building? Okay, how tall is this building? And we are told to take the acceleration due to gravity to be 9.8 meters per second squared. All right, so how do we set this up? All right. Now, one thing that we know is that at the moment when the ball hits the ground, it would have traveled through the entire length of the entire height of the building. Okay, so if we had the position function, let's call it x of t, and let x of t be the position of this ball at any time t, measured from the top of the building. If we have this position function, and if we knew that this ball will strike the ground at some time t star, right? Then if we wanted to find the height of the building, we could say that, oh, the height of the building would be the distance the ball has traveled at t star, because it would have completely gone through the entire building in terms of its height. Okay, so our goal is to find the position function and then determine the time exactly when the ball hits the ground, and then use the 2 to calculate the height of the building. All right. Okay. So how do we find the position function? Now, if a ball is falling from a height, it's falling to the ground, we can assume that it is going to move at the acceleration due to gravity. In other words, its acceleration will be similar to that which is dictated by gravity. Now, of course, the ball is going to experience some air resistance, right? Which is going to, alter its motion. But for the most part, we can assume that, that whatever resistance is going to face is going to be small compared to, the acceleration that is going to come from gravity. And so that is going to be the main force that is going to pull this object down. It's going to be the full weight of acceleration due to gravity. Okay. And so if we assume that, and we know that, well, my acceleration due to gravity is 9.8 meters per second squared, then we know that at every point in time, the x dt squared, which is the acceleration of the object, should be 9.8. Okay. If we assume that the object is falling at the acceleration due to gravity, it's accelerating, purely due to gravity. Okay. And so if we write this down, then this becomes our differential equation, where the differential equation has that physical law underlying it, right, that the object is moving at acceleration due to gravity. Okay. So that's our differential equation. Now let's look at the information we are given. We are told that it falls with an initial speed of 10 meters per second. So we can assume that the initial velocity, right, is 10 meters per second. Okay. Now, because it's a second order differential equation, we need an extra condition to find a particular solution. So let's see, what else do we know? We know that the ball is thrown straight downward from the top of the building. All right. So if x of t is measuring the distance traveled by the ball at any time, then what do you think the distance traveled by the ball at time 0 would be? Correct. Yes, 0, right? Because it starts from the top of the building, right? So this is going to start with at 0 meters, right? And so these two conditions will form our initial condition. Okay. So now we have an initial value problem, which we will expect to find. We expect to find one solution that can help us to identify what the height of the building is. All right, so let's go ahead to solve this. We know we can go from the second derivative to the first derivative by applying one integration process. So this is 9.8 dt, and this would be 9.8 t plus some constant c. Then if we apply this a second time, we can get our position function, right, which would be the integral of 9.8 t plus c dt, right, which will be 9.8 t squared over 2 plus ct plus some constant d. Okay, so we can simplify that. Say that my x of t is 4.9 t squared plus ct plus d. Okay, so now we have our position function, except that this is the general position function, right? This is just a general solution. We need a particular solution, right? So we'll go ahead and apply our initial conditions. We know that initially it starts from the top of the building, which means that my d has to be 0, right? And then we also know that the initial velocity is 10 meters per second. And so we can apply that to my my velocity equation here, right, and say that my c should be 10. Right? So that now my particular solution is going to be 4.9 t squared plus 10t and then plus 0. So here we have it. That's our particular solution. And this function is telling me the distance traveled by the ball at any time t. Okay, so now what remains is that if I want to know the height of the building, then I need to know when the ball strikes the ground. Okay, so how do I do that? How do we figure out where the ball strikes the ground? Let's try and create some space here. Well, what do we know about when the ball strikes the ground? Right. We know that the velocity of the ball is 60 meters per second. Okay, so we can use that. We know we have the velocity function. Right. We know that the velocity at any time t, right, is given by 9.8 t plus c, which we know to be 10. Right, and so if I know that the ball strikes the ground when it's moving at 60 meters per second, we can just set this to equal 60 and then solve for t. Okay, so that we have t being 60 minus 10 over 9.8, and that gives us 5.1. Okay, and so now the height of my building will just be the position function evaluated at 5.1, right, which is 4.9, 5.1 squared plus 10, 5.1, and that gives us 178.45 meters. Okay, and so we expect that this is the height of the building. Okay, so we've done a couple of things here. We have been able to formulate a differential equation from a physical process by applying a physical law, right? We came up with a second order differential equation. We have been able to translate the dynamics of the problem to give us initial conditions so that we could formulate an initial value problem. And then we've gone ahead to now solve this initial value problem by applying successive integration processes to find the unknown function, which is the position function. Okay, and then we've gone ahead to make predictions using this position function. This is the whole cycle of mathematical modeling in this example right here. All right, and this is what happens, you know, in practice every day with people who are into mathematical modeling. Okay. All right, good. Now, what do we do if, you know, the normal form of our differential equation is not conveniently just a function of x, right? So particularly, what if we have dy dx equals f of xy, and f of xy is not just a function of x, but it also depends on the unknown function y, right? Clearly, we cannot just blindly do an integration, right? Because we're going to have two unknowns here, and we wouldn't know which one to integrate with respect to. Okay, so we'll have to think of something else to do in this scenario. Now, in the next lecture, we'll talk about analytical methods to deal with this situation where the function is no longer, you know, this f here is no longer a function of this x. But for now, there's something graphical that we can do that can give us a sense of how the general solution looks like. Okay, so this graphical method is not necessarily going to give us like values that, you know, it's not going to spit out values for us. It's not going to give us a continuous function. It's not going to do that. What is going to show us are the graphs of the functions that lie in the general solution. Okay, and it can even show us the graph of a particular solution. You will not have the rule for the function in your hand, but you'll be able to visualize its graph. And based on its graph, you can make some predictions about the physical situation. Okay, this is a very, very useful method. And this is one of the methods where you are going to make use of Mathematica. So if you haven't already watched the video introducing you to Mathematica, I do urge you to watch it. I think it's about a 30-minute video, just to get familiar with how the language is designed. But we're going to use Mathematica to solve first-order differential equations graphically. Okay, so I'm going to take you through how that works in the next section of this lecture, and then we'll take some examples. Okay. And so our problem is a first order differential equation, right, where the non-derivative expression is not simply in terms of the independent variable x, but also in terms of the unknown function y. Okay. So how do we deal with this? We're going to use what is called a slope field to visualize the curves in the general solution. Okay. So very briefly, let me describe to you what a slope field is. Okay. Now we know that our solution to the differential equation, since this is the first order differential equation, it lies in the xy plane. So x is some input, y is the output. Okay. Now, if you imagine that we partition this plane into a grid, right, so that we are sampling just discrete points. Then at any point, let's pick one point here. Let's call this point xi, yi. Okay. At any point here, I can use my differential equation to calculate the derivative of my unknown function, because that is exactly what the differential equation tells me. Okay. If I calculate dy dx at xi, yi, the differential equation says this should be f evaluated at xi, yi. Now, this is a real number. And this f we know because we have the differential equation. Okay. And so one hidden secret in the differential equation, at least a first order differential equation, is that we actually know the slope of any function or of any curve in any function in the general solution at any point in my domain. Right? And we can use the differential equation to calculate this. Okay. So we can do this for any number of points. So I can pick, a few more points. I can pick a point here. I can pick a point there. I can pick a point here. And I can calculate the slopes at all of these points. So let's say that the slope here, looks like that. Like let this be the tangent line that has the same slope as my function. And let the slope here be like this. And the slope there have that. And then the slope here have this tangent line. Okay. If I should plot out the slopes at all points on this grid, what I'm going to generate is the slope field. Okay. And by looking at that slope field, because the slope field is basically giving us the tangent line at every point on my grid, you can begin to see trends. You can begin to see how your family of solutions will behave, because you can see the direction in which these slopes are. Okay, so just by looking at the slope field, you can have a sense of how the family of solutions are behaving because of the direction of the slopes. Right? You can look at how the group behavior is like. Okay. Now, if you want to visualize a specific solution, right? So you want to pick out some particular solution, right? One thing that you can do is just to, at every point, right, you just draw a curve that simply touches your tangent line. And you can continue to trace out this point, and connect all the dots. And as you do that, you are tracing out what is called the solution curve. And so this solution curve will be for some particular solution, right? And you can do this for multiple solutions within your family of solutions, and then you can have also that as a visualization. And based on that, you can say a lot of things. So for example, if this happens to be my solution curve, I can already see that there's a maximum occurring somewhere here, right? I can say a lot about how this function behaves towards infinity. I can say what happens towards minus infinity, right? If there are any critical points, I may not be able to pin them out exactly, but I can say approximately where they occur, any local maxes, any local mins. So there's a lot that can be said about the about the solutions to the differential equations without actually finding them, without actually calculating a continuous function that defines them. Okay, and this is the power of slope fields. Okay, it gives us a qualitative right, a qualitative assessment of the family of solutions and any particular solution that we want. Okay. Now, of course, if I were to ask you to do this by hand, that would be grossly unfair, right? Because you would have to plot out, slope fields for a lot of points, and then try and trace points that connect. I mean, that's just not feasible. And so we don't do this by hand, just because of the sheer volume of points that we have, sheer number of points that we have, and all the calculations that need to be done. We calculate slope fields using computers. Okay, and for this class, we are going to use Mathematica to do this. Okay, and so in the next slide, I'm going to show you. I'll first show you how a slope field looks like in Mathematica for a specific first order differential equation. And then I am going to explain to you how you can generate your own slope fields given any first order differential equation. Okay, and also how to generate the solution curves yourself. And you're going to use this in your homework problems to say something, something intelligent about, differential equations that we cannot solve by hand. Okay. All right. So here we have a differential equation here. This is a first order differential equation. Let me write this out in full so you can see it in all its glory. This is dy dx is equal to x. Okay. Now, of course, we know we can do this by direct integration. And I picked this specifically because we can at least compare what we are seeing from the computer output to what we know to be true, right? So if we were to solve this by direct integration, then we know that, oh, my y of x should be x squared over 2 plus c, right? So we have some scaled parabola that is shifted up or down by a constant c, right? Now, if I use Mathematica to plot the slope field, you can already begin to see from the slope field that you are having some kind of parabolas. Because if you look at the direction of all of these tangent lines, right, they seem to be tracing out parabolas. And in fact, if I now generate solution curves on the slope field, you can see that I have parabolas, right? And these are parabolas that have been scaled, and I'm just moving them up and down the y-axis. And that's what this constant c is doing. Okay, so this tells me that my family of solutions are simply scaled parabolas that are shifted along the y-axis. This is beautiful. This is beautiful graphical information about the family of solutions, right? And the most fascinating thing is that we can still generate these two things without having a clue about how my function actually looks like. That is actually the more useful, what is most useful about slope fields. Okay. All right. So now let's go into answering the question, how do we actually go ahead to generate, first of all, these vectors, right, that have slopes equal to, the tangent line along the curve at every point? And then how do we go ahead and trace out these solution curves in the slope field? Okay, so the slope field is actually very easy to generate. So this is my differential equation, dy dx, and this is equal to x. This is supposed to be the slope of each of these lines. Okay, so really all I'm looking for is that at every point xi, right, so I know that my tangent line xi, yi should have a slope of xi. All right. So how do I construct, if I have a fixed point, right? Let's assume that we have scaled back to 0 here. So if I'm at 0, and if I want to construct a vector that has a slope of xi, what can I do? Right? Remember, your slope of a line is rise over run. Okay. And so if I want to have a slope of xi, then I better rise xi units and run 1 unit. This way, the vector that I generate will have a slope of 1. I mean of xi. Okay, and this is the information that we enter into Mathematica. We tell Mathematica that at each point, generate a vector 1 and xi at every point, right? Or generate a vector that has the same direction as the vector 1 xi. And the computer is able to translate this information and then plot all of these vectors at every point on your grid. And that gives you your slope field. Okay. And then, of course, if you wanted to generate the solution curves, you can give it a different command. Okay. All right. So hopefully that is clear. And so what I'm going to do now, we're going to now transition into Mathematica. I'm going to show you how the, you know, how the program looks like and exactly what commands I enter into the program to generate the slope field. So this is the interface of Mathematica. Now, if you've already watched the video, right, Mathematica is really a giant graphing calculator. Okay, and just like how you interact with your graphing calculator, you can tell Mathematica to do plots, to do derivatives, to do integrals, to solve equations, to solve system of equations. Anything that you can do with a graphing calculator, you can do with Mathematica and more. All right, so you can use it from that perspective of being a purely being a graphing calculator, essentially. Okay, now it also has the added advantage that you can actually write computer programs. So you can write scripts using a combination of functions that have already been built in Mathematica and ones that you create yourself. You can actually instruct the computer to perform specific tasks over and over and over again. Okay, so there's a programming component to Mathematica, which is also present in your graphing calculators. You can program your graphing calculators to perform statistical analysis and solve linear programming problems. You can do the same thing here with Mathematica, but except that this gives you a much bigger platform to do it. So if you can use a graphing calculator, you can use Mathematica. This is nothing to be scared about. The most important thing is for you to understand the basic structure of the program. So please make sure you watch the video on Introduction to Mathematica. That will help to give you a solid foundation. And then as we go through the class, I will introduce to you different kinds of functions that you can use to perform different tasks. And your job is just to replicate them and customize them for a specific problem at hand. Okay, but you're definitely free to explore outside of what I show you because there's so much more that it can do. All right. Okay, so in order to generate a slope field, I use an inbuilt function in Mathematica called vector plot. So its name does exactly what I wanted to do. It plots vectors on a grid. Okay, now in Mathematica, anytime that you use a function, whatever you want the function to do is going to be contained within square brackets. So you have these square brackets here. This is the end of the function. This is the beginning of the function. Okay. So functions always open with square brackets and they end with square brackets. Right. And then inside of those square brackets, you are going to describe exactly what you want the function to do. Right. Now for vector plot, the first argument is your vector that you want to plot. So in our specific problem, the vector we wanted to plot was 1 and x, right? Reason because my differential equation was dy dx equals x. Well, if my differential equation happens to be dy dx equals f of xy, what vector do you think I'll be plotting? Right? Again, if I want my slope to be f of xy, then I have to rise by f of xy and run by 1. Okay, and that will give me the vector. All right, and so I will be plotting the vector 1 and then f at xi, yi. So this can always be customized by replacing this x with whatever your f of xy is. Right. So that's the first argument. The second argument is the range of x values that you want to show on your grid. So notice that here my x-axis ranges from -4 to 4 because that is what I told you to do. And so it's going to take this range and it's going to create a grid at discrete points. So look at all these tick marks here. This is how it constructs the grid, and that's how it formulates the slope field. Okay, so you have to tell it what range of x values you want. Okay, and then you also have to tell it what range of y values you want to see. Okay, and again, that range is represented here. That is 4, and you have a 4 down there also. Right, so those are the first 3 arguments. This is the first argument, the second argument, the third argument. Now, the fourth argument, you are now going to specify how you want your vectors to look like. Okay, so this option, vector scale, allows you to control the size, the size of your vectors and their orientation. Okay, and so you can control the size by this size parameter here, which is the first argument of the vector scale option. Okay, if you make this argument larger, your vectors become larger, and I'm going to illustrate that. So let me change this to 0.3 instead of 3. Anytime you want to evaluate a function in Mathematica, and you're going to learn this from the video, you're going to use Shift Enter. Okay, so Enter will not evaluate a function. It's just going to go on to the next line. But if you want Mathematica's brain to actually perform an operation, you have to use Shift Enter. So I'm going to position my cursor right at the end of my function, and I'm going to press Shift Enter, and it's going to regenerate my slope field. So look, right, that my vectors have become much larger at each point. Okay, and I can make them much smaller. If I make this 0.003, and again I do a Shift Enter, now my vectors are much smaller. Right. So you control the size of the vectors using this first argument of the vector scale function. Okay. The next 2 arguments you don't really need to change much, right? You can just keep them as automatic and none. They control the what is called the aspect ratio of the vectors to the grid. Okay, so it just controls how they scale relative to the grid, right? But it's easier. Automatic allows the computer to do it by itself, right? So that you don't force it to do something that you don't want it to do. So you can just focus on manipulating the size of your vectors. Of course, if you want to learn more about any function in Mathematica, what you need to do is to go to help. So if you go to the help menu and you type Wolfram, you click the Wolfram documentation, it's going to open up a documentation center that, it's like a library of information for you. So if I want to know tell me about vector scale, and I press enter, it's going to pull up all of the information that Mathematica has about vector scale and how to use it. Let me clear the screen. Right. And so notice that it brings up vector scale, and then it walks you through the details about how, vector scale works, right? So if you open up these details, you can read about what the different, components mean. And then you can go and look at some specific examples of slope fields and how they have used the vector scale function to control the vectors. And then when you're done, you just close the documentation center. Right? This is the fastest way to learn Mathematica. You will not be able to know all the inbuilt functions that are available. You just learn them when you need them, right? And you just go and type them and you can learn more about them. Okay, so that's about the vector scale option here, right? The next option is more of aesthetics, okay? And that also controls the option is the vector style, right? And you can use the vector style to change, for example, the color of the vectors. Right? So if I don't want them to be in blue, I can decide to change them to red, and then all my vectors will be in red, right? I can also play with the size of the arrowheads. If I want them to be larger, I can just reduce this ratio, and my arrowheads become way larger. If I want them to be teeny weeny bit smaller, I can make this much smaller, and then I can almost not see the arrowheads anymore, right? And you can play with this until you find one that is right for your problem. Right? So you can adjust the color, and you can also adjust the size of your arrowheads. Okay, and then that's it. That's all. Most of the things that you need to play with. The rest, you just press Shift Enter, and then it displays your slope field. Okay. All right. So that's it for the slope field. Now, if I want to introduce solution curves, I have to introduce a new function called stream plot. Okay, the stream plot function in Mathematica is going to trace out your solution curves for you. Okay. Now, just like vector plot, you need to enter the vectors at each point so that it knows where they are. You need to enter the range of x values, the range of y values. Okay, and then you need to enter how many solution curves do you want to see. Right. So this stream points option allows you to specify how many solution curves you want to see. Remember, this is the whole family of solutions. All right. So I can decide that, okay, I don't want to see 10, I just want to see 5. I can change this to 5, and then it's going to show me just 5 solution curves. Or I can say that, okay, I want to see 50, and it's going to show me 50 solution curves. And that almost looks like a fingerprint. Okay, cool. So you can control how many solution curves that you want to see by just changing the stream points option. All right. You can also control the color and the thickness of your curves by using the stream style option. All right. So here I specify that I want them to be blue. I can change them to red, green, black, whatever I want. If you want your curves to have direction, you can specify arrowhead so that it tells you what direction that you're moving in. Right. So for example, I can set this to 1. And then, oh, that's too big. So let's make it 0.01. Right. Now, notice that it's drawn, make this slightly bigger. It's drawn arrowheads on my solution curves just to show me what direction my curve is moving in as x values increase. Right. So you can do that or not. You can just set this to be 0, and then there are no arrows on your solution curves. All right. And then you can also play with the stream scale option, right? Which also adjusts the size of your solution curves. So you can change this from medium to small to large. And if you have a specific number that you want to use to specify, you can also specify that. All right. So that generates the solution curves. All right. Now, these solution curves are separate from the slope fields. Okay, the picture I'm showing you here, I have superimposed the solution curves on the slope fields. Okay, now the way to do that in Mathematica, if you have 2 different plots and you want to superimpose them, you're going to use the show function. Okay, and then you just enter. So notice that here I set my stream plot to this function strip, and then I set my vector plot to be equal to this function VTP, and now I'm showing VTP and strip. That superimposes the two plots. Okay, if I don't use that option, it's going to show me two separate plots. So it's first going to show me the slope field, and then it's going to show me the solution curves without a slope field. Okay, but my goal is to see both, and so I use the show to give me both. All right. Now notice that I played around with the semicolons at the end of my function definitions a bit, right? These semicolons are called suppressors, and essentially you can use them if you don't want to see the output from a function. You can use a semicolon to suppress the output, right? So if I put a semicolon after the show function, it no longer shows me the graph. If I remove the semicolon and I press Shift Enter, it displays the graph, right? And then you can stretch this graph to any scale that you want, make it bigger or smaller. All right, so this is how I generated those solution curves combined with the slope field. Okay, now there's even more that you can do. Now, if instead of visualizing the whole family of solutions, or at least 10 of the functions in the solutions, you are only interested in visualizing a particular solution, right, for an initial value problem, you can also do that. Okay, so let's suppose that my differential equation has initial condition that y of 0 is -4, which means that the point 0, -4 has to lie on my solution curve, right? And so if I want to do that, then I will just adjust the stream points and just tell it to plot this point 0, -4. Okay, and so once I do that, it's only going to show me just one plot, and it's going to be the only function that goes through the point 0, -4, and this is my particular solution. Okay, so you can also do that. You can also visualize particular solutions using Mathematica. Right, now if you want to say now, copy this output and print it, or for your homework, right, if you go to the sidebar to your right, notice that when my cursor gets to this sidebar, it turns blue, right? If you right click this sidebar, it gives you options, right? And it allows you to save the plot and do a bunch of other things. Okay, you can print it, you can save it. So I can print selection, and it's going to print my plot. I can save it to a file. I can copy it and take it to PowerPoint, for example, and do other things with it. So this is an image that you can always get out of Mathematica by either printing it out or just saving it as a PNG or a JPEG, and then you can attach it to your reports for your homework. All right, so that's it. This is how you generate slope fields and solution curves using Mathematica. Now let's go back to our presentation and take an example. All right, so here's a specific scenario here that we would like to use slope fields to get some qualitative information. We are considering the differential equation dv dt equals 32 minus 0.16v. Okay, notice that this is a first order differential equation. Okay, now if you look at your right hand side, this is not a function of the independent variable t, and so we cannot directly integrate this to find a solution. Okay, and so at this point in time, what we can do is to visualize the slope field and possibly solution curves, and that will give us a sense of what is going on. Okay, now this differential equation is describing the speed or the velocity. I guess in this case it's scalar, so this is really just the speed. the speed of a baseball thrown from a helicopter that is hovering at 3,000 feet above the ground. Okay. Now imagine that you throw this baseball with some initial velocity. Okay. And the differential equation is modeling the speed of the baseball at any point in time. Right. Now the question is to use slope fields to estimate the speed with which a receiver on the ground should expect to catch the ball. Okay. And the question is, does the terminal speed of the ball depend on the initial speed with which we throw it? Now, whatever speed that the receiver is going to catch the ball at is going to be around the terminal speed. And I'm going to explain what the terminal speed actually means. For those of you who have done some physics, you probably have an idea what the terminal speed is. Okay. But the idea of terminal speed is really that you throw something from a height above the ground. Because of the presence of air resistance, eventually that object is going to move at a constant velocity. Okay, and so that's really the velocity that we are trying to estimate, so that we know, what speed to expect the ball to be at when we are on the ground. Okay. And we are leaving the initial condition open. We are assuming that the initial speed is arbitrary. And so we really want to get a sense of how the family of solutions behave. And we want to see, well, if we change the initial speed, how does it affect the dynamics of the problem? How does it affect the terminal speed of, of the ball as it hits the ground? Okay. All right, so we are going to visualize this using slope fields, and we are going to plot at each point the vector 1 and 32 minus 0.16 VI. Okay, so let's go to Mathematica and do this. All right, so let's look at our example here. Okay. So notice that I have entered the vector that I want Mathematica to plot at every point using my differential equation. Okay, and I've entered the same vector in the stream plot option. And I've told it to run the time. So here my x-axis is time, and my y-axis is velocity. Okay. So my time runs from 0 up to 50. My velocity also runs from 0 up to 50. Up to 500. Okay, so these velocity values I'm going to use to essentially try and analyze the system, what happens to the terminal velocity for different values of the initial velocity. Because I'm going to allow that to be the range for velocity, and then I've set options for the vector scale and the vector style. The same thing for the stream plot. Okay. Now the cool thing here is that I can now test different initial conditions. All right, and then see how the solution curve looks like. Okay, so here I specify that I want a solution curve that at time 0.1 it's around 200 feet per second. Okay, so this 0.1 is somehow close to 0. So I'm trying to, by using this point, examine what the solution curve will look like if I should throw my ball from the helicopter at 200 feet at a speed of 200 feet per second. Okay. Now, if I visualize that, just taking 200 feet per second, this is my solution curve. Okay. Now notice that my solution curve is a straight line, which means that if I throw my ball from the helicopter at 200 feet per second, it stays at 200 feet per second until it hits the ground. Okay. Now, on the contrary, if I decide to throw my ball at a slightly higher speed, say at 300 feet per second, right? So this is the solution curve for 300 feet per second. Notice that the speed, gradually decays, but then it approaches 200 feet per second. Right. So in other words, the speed of the ball will decrease towards 200 feet per second. All right. If I decide to throw the ball instead of 300, I throw it at 100. So I'm testing this point here. Right. Now again, my speed increases up to 200 feet per second. Okay. So this tells me that, well, 200 feet per second appears to be some kind of asymptote, some kind of horizontal asymptote that eventually, whether I start from 300 feet per second or 100 feet per second, that my speed eventually gets closer and closer to 200 feet per second. Okay, so that tells me that 200 feet per second is really my terminal velocity. Okay, and that is the reason why when I throw the ball at 200 feet per second, it stays there. Right, it doesn't change because that's like an equilibrium state for the speed, and that's exactly when the forces that are driving the motion balance out the air resistance and other forces that are opposing the motion. So you have a net force of 0, and so you have a constant velocity. Okay, so that appears to be my terminal velocity. And I can try a few more numbers. So let's say we start from 400 feet per second, and then we go a bit lower to 50 feet per second. Right, the same thing happens at 400 feet per second. The ball will decrease its speed and then try and approach 200 feet per second over time. And then the same thing happens if I throw at 50 feet per second, the speed increases, right? And that drives it to 200, and then it becomes steady. Okay, and so this tells me that, well, if I'm on the ground and I'm above 3,000 feet above the ground from the helicopter and this ball is thrown, we can expect that whoever is on the ground is going to catch this ball at around 200 feet per second, right? And that is valuable information that we have obtained by just playing around with different initial conditions and looking at the solution curves without actually calculating the continuous function that is the solution itself. This is how powerful slope fields can be in solution curves. And so I would ask you to do this kind of analysis by just looking at trends in your solution curves by plotting these graphs. Okay. All right, so let's go back to lecture. So we've seen how we can use slope fields to solve first order differential equations by visualizing the solution curves. Okay, right, now to a very important question. How do we know that, so given an initial value problem, how do we know whether it has, well, first of all, whether it even has a solution? Because we've already seen from the very last lecture that not all differential equations have solutions. So how can we check to see if it has a solution? Can we tell if it has just one solution, which will make the solution unique, or if there are infinitely many solutions? Now, our preference for initial value problems is that we have a unique solution. Okay, and so we're going to look at 3 different scenarios of what could happen with an initial value problem, and then we are going to use a theorem to explain what is going on. And then based on that theorem, you will be able to tell ahead of time if a differential equation, a first order differential equation, will have a unique solution or not. All right. So let's take example 5. Examine whether a solution exists for the initial value problem below. If a solution exists, how many can be expected? Okay. All right. So we have dy dx is 1 over x, right? Now, because my right-hand side is only a function of x, I know that I can solve this by direct integration. Right? And so my y of x is the antiderivative of 1 over x dx, which is a natural log of the absolute value of x plus c. So this is my general solution. Okay. Now notice that this function is not defined when x is 0. So this is only defined when x is not 0. Because of the absolute value, we can afford to evaluate the natural log at negative numbers. Okay, because it's going to be absolute value anyway. So this function is continuous for x different from 0, but then our initial condition is specifying a value for the function when x is 0, right? Now clearly there's our general solution does not allow for x to be 0, so we could not possibly pick a particular solution that would have a value of 0 when x is 0, right? And so because of this, the initial value problem, y prime equals y of x, where y of 0 is 0, has no solution. Okay, so let's call this case 1. Now let's look at another initial value problem. Okay, so now we have dy dx is 2 square root of y. Okay. Now, unfortunately, this is not of the type that we can do a direct integration, because my right-hand function here is not in terms of the independent variable x, it's in terms of the dependent variable y. But we're going to find out very soon that we can solve problems like this. Okay, so I'm going to just go straight ahead and put down what the solution for this problem looks like, and then later on we will verify it. Okay, so the general solution has the form y of x equals x plus c all squared. Okay, we can verify that this is true by differentiating that. So this is 2x plus c, right? But then x plus c is the square root of y, so this is 2 the square root of y. So clearly this function satisfies my differential equation, and since it depends on it satisfies it regardless of the value of c, it makes it a general solution. All right, so this works. Now we want a particular solution that satisfies the condition that when x is 0, y is 1. All right, so let's try and see whether we can plug that in. Fortunately, this function is defined for all real numbers, so we can afford to try and find a particular solution. This is 0 plus c squared. This should be 1, right? And so that implies that my c has to be 1. And so my particular solution is x plus 1 all squared, right? And I have found one. Okay, now this is the only function that will satisfy that differential equation, that initial value problem, which makes this a unique solution. There is only one of it. There's a unique solution to the initial value problem. Not the differential equation, but the initial value problem. Okay. All right, let's look at the final example. So we have dy dx being y to the 1/3. Okay, now again, this is not of the form where we can apply direct integration, because the right-hand side is not a function only of the independent variable, but we can verify that the function y of x, which is 2/3 x plus c to the 3/2, actually solves this differential equation. Okay, so let's do that. Y prime is 3/2, 2/3 x plus c. Now, if we subtract 1, we have 1/2, and this is now times 2/3. If we simplify that, my y prime is now what? 2/3 x plus c to the 1/2 power. Okay, now notice that this is the same as the cube root of 2/3 x plus c to the 3/2 power. Okay, and so my y prime is actually the same as y to the 1/3. which is my differential equation. So this satisfies the differential equation. And this function is defined for all real numbers because we are taking, well, we are taking the square root of the cube of the function. And so we do need to make sure that the cube comes out to be positive before we can go ahead and take the square root. But in any case, it is clearly defined when x is 0, right? So we can go ahead and attempt to find a particular solution for this. Okay, so we want y when x is 0 to be 0. So we want 2 over 3 times 0 plus c to the 3 house, right? We want this to be 0, which implies that my c has to be 0. And so a particular solution to the initial value problem is 2 over 3x to the 3 house. Right. So I have found one solution out of my general solution. Okay. Now there's a surprise. Okay. Consider the function y of x that is always 0. So it's 0 for all x. Okay. Now notice that my derivative of that function is also going to be 0 for all x. Okay. And if my function is 0 for all x, then clearly it will satisfy the differential equation because dy dx is supposed to be the cube root of y. But if my function is 0, then dy dx is 0. And the cube root of 0 is also 0. Okay. So this identically 0 function also satisfies the differential equation. And in actual fact, because the initial condition is saying that the function should be 0 when x is 0, and the function is always 0, then it also satisfies the initial condition. And so the function y of x, which is identically 0, is also a particular solution of my initial value problem. And so I have just constructed two particular solutions to the initial value problem. Okay, and so this is something that we, in practice, we actually do not want. We don't want to have an initial value problem that has more than one solution. Okay, and so if we were to say formulate a differential equation from a real life process and come up with, you know, such a solution, we would have to want to go back and rethink our formulation because we expect that there's only one possible path that the dynamics can take if we initialize it at some point, as long as, you know, there's no randomness in the whole problem. And so we don't want this, and we don't want this case also where there's no solution, because if we formulate an initial value problem that has no solution, then really there's nothing that we can use to make predictions. So what we want is for it to have a unique solution, right? And so we do need to have a way that we can separate out the cases where there's no solution and the cases where there's more than one solution from the cases where there is a unique solution. Right? And that is the theorem that we're going to discuss next. Okay, so what is this theorem saying? If we have an initial value problem, dy dx is f of xy, and let's assume that the initial condition is y of a is b. All right. Then a couple of things. What are the assumptions? One, if we assume that the right-hand function f is continuous. Okay. And it's continuous specifically within, so let's call this y and let's call this x, and let's say that this is my initial point AB, which determines my initial condition, right? So definitely I want my solution curve to go through this, my particular solution, okay? Now I want my function f of xy to be continuous within some rectangle that contains my initial point. Let's call this rectangle R. So I want this to be continuous in R, okay? I also will assume that the partial derivative with respect to y, the unknown function of this f here, is also continuous in this rectangle here. Okay, if these two assumptions are satisfied, then the theorem asserts that I have a unique solution for my initial value problem. Okay, and that unique solution can be defined within some interval around my initial point. So this is a minus some epsilon, and this is a plus some epsilon. Let's call that interval I. It's an open interval. So there is some unique solution in I. Okay, and that's all that the theorem can guarantee, that you can only go this far to the left of A and this far to the right of A and have a unique solution. Different things can happen if you go outside of that interval about A, but at least you're guaranteed that you can find some interval around A where this function has a unique solution. Okay. And so this is our theorem, right? So what we're going to do next is to try and apply this theorem to the examples that we have and see whether we could come up with the conclusions that we determined. Okay. Now, one thing to keep in mind is that because this theorem is an implication that some logical statement P implies a logical statement Q, if P is not true, right? So if P is not true, then we cannot expect this result to hold. Okay, but this P here is a compound logical statement. It's an AND statement. So there are two things that have to be true here. So if any one of these two things are violated, we cannot expect this implication to hold. All right. So keep that in mind as we go through it. Okay. So let's check what we had for example 5. We had the differential equation dy dx is 1 over x. We had the initial condition y of 0 is 0. Okay. Now my f of xy is 1 over x. The partial derivative with respect to y is 0 because this doesn't contain y. My initial point is 0, 0. And so for me to have a unique solution, I need to be able to show that, let's put 0, 0 here. I need to be able to show that both of these functions are continuous around 0, 0. Okay. Now, clearly, 1 over x is not continuous at 0. Right? It's undefined at 0. And so if it's not continuous at 0, it cannot be continuous in some rectangle that contains 0 because it's going to fail to be continuous here. And so the first assumption of my theorem is violated, which means that we cannot expect a unique solution. And that's exactly what we had. In this first case, we saw that we had no solution. Okay, which clearly says that we don't even have a solution to begin with for it to be unique. Okay, so if we had used this theorem before actually trying to calculate the solution, we would have been able to at least identify that the problem had no unique solution. Okay, at this point, we would not have been able to say that it had no solution. We would only have been able to say that it doesn't have a unique solution. All right, let's see what happened in example 6. So there we had y prime equals 2 square root of y, and the initial condition was y of 0 equals 1. Okay, so my f of xy is of course 2y to the 1/2. Its partial derivative with respect to y, right? That's 2 times 1/2 y to the minus 1/2, which is the same as 1 over the square root of y. Okay. Now in this case, my initial condition is 0, 1. So right here, right? And I'm looking to argue that my function and its partial derivative are continuous within some rectangle containing 0, 1. Okay. So my function is, the square root of y, right? It's twice the square root of y. And we know that the square root of y function is continuous wherever y is positive. Okay. Now, all the way here in the upper, the upper half plane, y is positive. And so since this function is independent of x, right, it's continuous for every point above the x-axis. And so clearly, I can always be able to construct some rectangle R where this function is continuous. Okay, so this checks out. Right. Now the next function is 1 over square root of y, and this is y greater than or equal to 0. Right. 1 over square root of y is continuous wherever y is strictly greater than 0, because we cannot have y being 0 in the denominator. Now again, this is continuous for all points above the x-axis, not including the x-axis. And so we can definitely find some rectangle about the point 0, 1 where it is continuous. So this condition also checks out. And so these two conditions being satisfied then implies that this problem has a unique solution. Okay, and that's exactly what we found out. We found one and only one solution for that initial value problem. Okay, which is the best case scenario for mathematical modeling, that there's only one function that dictates the dynamics. All right, what about the final example? Example 7. So there we had two solutions, if you recall, and we want to see which of our assumptions failed. So we had dy dx is the cube root of y. And my initial condition was that y of 0 is 0. Okay. So my f of xy, of course, is y to the 1/3, which is independent of x. Right. Now, since this is a cube root, it is continuous for all real numbers. Right? Because you can take the cube root of a negative number. Okay. However, the partial derivative with respect to y, this is now 1 over 3 y to the minus 2/3, which is 1 over 3 times the cube root of y squared. Okay. Now, why is this function continuous? Since we are squaring y, right? This function is this denominator is defined as long as y is not 0. Okay. Because if y is any other real number, we can always square it and we can take the cube root. But if y is 0, then we're going to have a 0 in the denominator, and that will be undefined. Okay. So it's continuous as long as y is not 0. But our initial point is the origin, which has a y value of 0. And so clearly this partial derivative is not continuous at the origin. And so it cannot be continuous in any neighborhood of the origin. Okay. And so for that reason, this condition is not satisfied, and we don't get a unique solution. There's no unique solution. Which explains why we had 2 solutions in that example there. So this is a very powerful theorem. It can always tell you, when you can expect unique solutions. Okay. Now it can actually do a little bit more than that. So there's an extension of the theorem that can allow you to distinguish between when you have no solution and when you have more than one solution, because at least that is something that we would like to be able to distinguish between. And no solution case is more discouraging than having infinitely many solutions, because at least you know that there is some solution, right? So there's an extension of this theorem, which essentially says that, okay, if you have condition 1 satisfied, so if your f of xy is continuous in some rectangle, then you have a solution. So existence is guaranteed. Okay, you have a solution, but it is only when the partial derivative is also continuous that you have only one. All right. So that's exactly what this is saying here, that if my f of xy is continuous, then at least one solution exists, which is existence, right? But you only have uniqueness if you include, if you in addition you have that the partial is also continuous. Okay. And so you would notice that in the third example, we had the function being continuous, f of xy being continuous, but its partial derivative failed to be continuous. That's why we didn't have uniqueness. But we had existence, which means that we had at least 2 solutions there. In the first example, both of these guys were not continuous, and so we didn't even have existence, and that's why we had no solution. Okay, so this is how that you can use the extension of this theorem essentially to distinguish between cases where there's no solution or there's infinitely many solutions. Okay, and so with that, I think I'll wrap it up here and try out these problems. Practice the direct integration, which most of you should be familiar with. Now, in Calc 2, you learned a lot of integration techniques, integration of trigonometric substitutions and partial fractions and all of that stuff. Well, all those things are fair game here, because you should be able to find the antiderivative of any function whose antiderivative can be calculated. Okay, so just if you meet a function that you've forgotten how to find its antiderivative, just go back to your Calc 2 and review most of these special techniques for integration. But otherwise, that's all there is to it. You just have to do an integration. So practice those and then try out some of the application problems, and then test your understanding of this existence and uniqueness theorem. Make sure that you can classify initial value problems as having no solution, having a unique solution, or having more than one solution. All right, and so with that, I would leave it here, and then the next lecture we would now begin to focus on some other techniques for solving first-order differential equations. Right? So the only analytical technique we have so far is the direct integration. Right? We'll look at a few more that can be useful for specific cases. All right, guys, enjoy the rest of your day, and then look out for my final lecture for this week sometime today. Okay, take care. Bye.